Burn a diary, and physics says something strange. The diary is not gone. Every word is still there, scrambled into smoke, ash, and heat. And in principle, a perfect scientist could reconstruct every page. That is a law of the universe. Information can never be destroyed. Now, throw that diary into a black hole. Where did the words go? That one question started a 40-year war between the greatest physicists alive, and the black hole information paradox may end up rewriting physics itself.
First, the rule. Deep inside quantum mechanics sits a quiet, unbreakable principle. The universe keeps records. You can shred, burn, or dissolve anything you like, but the information describing it, every particle, every position, is only ever rearranged, never erased. Physics without this rule stops making sense. Cause and effect fall apart. Prediction becomes impossible.
Then black holes walked in and broke it. A black hole is the universe's perfect shredder. Whatever falls in, a star, a spacecraft, your diary, the black hole keeps no visible trace of it. From the outside, every black hole is described by just 3 numbers: its mass, its spin, and its electric charge. Physicists summarize this with a famous phrase: black holes have no hair, no texture, no memory, no fingerprints of anything they ever swallowed. For a while, there was a loophole. Maybe the information was not destroyed, just locked away inside forever. Then, in 1974, Stephen Hawking closed the loophole. He showed that black holes slowly evaporate, leaking faint radiation until, after unimaginable stretches of time, they vanish completely. And here was the killer. That radiation looked perfectly random, pure static. No trace of the diary, the star, or anything else. When the black hole finally evaporates, the locker disappears, and everything inside is simply deleted from reality.
Hawking said it plainly. Information is destroyed. Quantum mechanics is wrong. To most physicists, that was not a bold claim. It was a declaration of war. Because if information can be destroyed anywhere, even inside one black hole, then the mathematical foundation of quantum mechanics collapses everywhere. Probabilities stop adding up to 100%. The theory that gave us lasers, transistors, and every computer on Earth would be broken at its core. Physicists like Leonard Susskind and Gerard Hooft refused to accept it and spent decades fighting back.
The first great clue came from an unexpected place: the size of a black hole's memory. Jacob Bekenstein showed that a black hole's entropy, roughly the amount of information it can hold, grows with the area of its surface, not the volume inside it. Stop and feel how strange that is. Every storage device you know scales with volume. A bigger box holds more books. But a black hole's capacity is written on its 2-dimensional skin.
That discovery grew into one of the wildest ideas in modern physics, the holographic principle. Everything that falls into a black hole may be encoded on its surface, like a 3-dimensional image stored on a flat hologram. The inside might be a projection of information living on the boundary. The war even had a formal surrender. Hawking had famously bet the physicist John Preskill that information really was destroyed. In 2004, Hawking conceded the bet in front of the world's press and paid the agreed prize, an encyclopedia of baseball, from which, as the joke went, information can be recovered at will. But conceding a bet is not the same as solving a paradox, and the fight actually got worse before it got better. In 2012, physicists discovered that the leading rescue plans created a new monster. If information really does escape in the radiation, then the mathematics seemed to demand that the event horizon becomes a firewall, a wall of blazing energy that incinerates anything falling in. That directly contradicts Einstein, whose theory promises that crossing the horizon of a giant black hole should feel like nothing at all. Now physics faced a three-way collision: quantum mechanics, Einstein's gravity, and the smooth horizon. At least one of them, it seemed, had to be wrong.
The real progress came recently. Physicists calculated, step by step, how information could actually escape. The answer, hiding in the mathematics: Hawking radiation is not pure static after all. Woven into it are unimaginably subtle quantum correlations, each escaping particle secretly entangled with the others, together carrying the scrambled story of everything the black hole ever consumed. Follow the radiation long enough and the information comes back out. Not readable, not usable, but not destroyed. The calculations even reproduce the exact curve that quantum mechanics demands. The debate is not fully closed, but for the first time in decades, the scoreboard leans one way. The universe does not delete. So return to your diary, falling past the event horizon. It is torn apart, scrambled beyond any hope of reading, its atoms dissolved into the strangest fire in existence. And yet, page by page, particle by particle, its story leaks back out across eons, written in a code no one can crack, sprayed across the universe in whispers of radiation. The black hole did not erase your diary. It translated it into the most unbreakable encryption reality allows.
And that idea is bigger than black holes. It means the universe never forgets. Every word you have ever spoken, every choice, every heartbeat is information. And information is permanent. Scrambled, scattered, hidden beyond all reach, but never gone. The cosmos turns out to be less like a shredder and more like a library with no exit. Nothing that has ever happened can truly be undone. In a universe of dying stars and evaporating black holes, that is a quiet kind of immortality, and it belongs to everything, including you.
Now look up at the night sky, at the one object that has watched every page of human history being written: the moon. It feels permanent, eternal, untouchable. But what would actually happen if, tonight, it simply vanished? The answer is nothing like you expect. That is the story of the next video.